So let's take a look at this one. Now number 4, right? Number 4, we have a box being pushed along a rough floor. So what does that mean? That now we do have friction. All right, so now we do have friction, okay? But this is going to be tricky here, ready? We have a box being pushed along a rough floor, but you know what? We have constant velocity. If we have constant velocity, what does that tell you about your acceleration? Acceleration equals 0. Excellent. And guess what? If the acceleration equals 0, that means I'm in equilibrium. And if I'm in equilibrium, what does that mean about my net force? It means it is also 0. So anytime you see that constant velocity, what that means is we're not changing motion. We definitely have forces. There are forces happening. Just like the normal and the gravity, there are forces that exist, but if we're not changing our motion, okay, then the net force is 0. So let's talk about all the forces on here. What are we going to have? We have normal and gravitational. And we have applied to the right still, but now what else do we have? We have friction. Okay? So let's look at what's happening. If I'm looking at the net force in the y direction, okay, I have positive Fn, because it's in the upward, it's an upward vector, plus negative Fg, and that's going to equal 0 because my object is not moving up and down. So up and down, right, there is no change in motion up and down. So in the y direction, my net force is 0. However, in the x direction, so the net force in the x direction, I have positive Fa plus a negative force due to friction. But here's the thing. If I'm moving with constant velocity, that means what about the magnitude of these forces? If I'm moving with, they are equal to 0. So if I am moving with constant velocity and there's no acceleration, then they have to be equal to each other. Okay, so I have speed, but I'm not accelerating. I'm not getting faster. I'm not getting slower. So that would be me pushing this marker, right? There's friction, and I'm pushing, but I'm not changing speed, and that's because the friction and my push are the same value, right? But if I push faster, right, then my force is greater than the force of friction, and then it's going to accelerate. But if you're moving with constant speed, this net force is 0. And what that means is that Fn equals Fg and Fa equals Ff. So when I'm drawing my free body diagram, if I draw on a dot, it's going to be the same size up and down and the same size left and right. So this is applied force, friction force, normal force, gravitational force. And what was the key word in here again? Can you guys tell me? What was the key word that made me know that the vectors for applied and friction were going to be the same size? The constant velocity. Constant velocity. So if you are not changing speed, so you're either at rest or constant velocity, that's when the net force is 0. If the net force is 0, it's because the force vectors are the same size in opposite directions. All right. For number 5, we have an object. Oh, actually, let's go back to this. Actually, we'll wait for it. Well, I'll put it on this one. I have an object that slows down due to friction. Okay? So what are the 2 easy peasy forces that we have? normal, and gravitational. All right, and what is the other force I have to have? Friction. Okay. Now, do you guys see the wind behind the box? Right? So what direction is it implied that this is moving? What direction do you think this box is moving? To the right, yeah. The box is moving right. Now, you actually need to know this piece of information, okay? Because if the box is moving right, where's friction going to be? Friction needs to be to the left, okay? So the one big thing for this diagram is we need to know that the force of friction always points opposite the direction of the motion. So since we're moving to the right, friction has to be to the left. Okay, what do I know about the sizes of the normal and the gravity force? They have to be the same. And then friction, we can draw that whatever size we want. Okay, so let's talk about the net force. So the net force in the y direction is obviously going to be what? For the up and down, what's the net force? It's going to be 0 because we're not accelerating upward or downward. So the net force is 0. For the x direction, though, can someone tell me what the net force is? We have to add up all the vectors in the x direction. How many vectors do we have horizontally? We only have the one. What is that vector? What kind of force? Friction. Is it moving to the right or to the left? So what should we write for net force? Negative friction. Okay? So the net force is negative friction. So friction, maybe it's 10 newtons. What's the net force? Negative 10 newtons. So when we talk about forces, like if I say, hey, how much force does friction have? Or how much force is the applied force? How much force is this or that? You just say the magnitude of it. You say, oh, that's 20 newtons. That's 50 newtons. That's 200 newtons, right? You just give the number value. It's not until you're doing the net force that you're assigning a direction to it. So generally, down and left are negative, up and right are positive. So here, what this means is that I have negative force, okay, which means what direction is my acceleration? If I have a negative force, it's also negative. So the acceleration is also negative. And the reason why is because force and acceleration are always in the same direction. Force and acceleration are always in the same direction. Now, what motion was I moving? Where was I moving? The box? The box is moving to the right. The force and acceleration are to the left. So what does that tell you about what's going to happen to the box? It's going to slow down to a stop. Right? Because when your velocity and acceleration are in opposite directions, you're slowing down, okay? So even though we're moving to the right, our net force is to the left. So our force and velocity, right, the force and the motion do not need to be in the same way, but force and direction are always in the same direction, force and acceleration, all right? And last example, we have an object falling, and it's increasing in speed. So what two forces must we have on here? We have a gravitational force. And because they don't mention it, what must we also have? Think about when you're falling through the air. You're going to have? I know, because I asked you to cross that out. Air resistance. Good. And what do we call air resistance? FD. Okay, now if we are increasing in speed, what does that tell you about your net force? If you're getting faster, are you changing your motion or is it constant? We're changing it. So my net force is not equal to 0. What does that tell you about the size of these vectors? This should be D for drag force. What does that tell you about the size of the vectors? Can they be the same size? No. So we have different size vectors. And what we know is that the gravitational one, because we're increasing in speed and we're going down, the gravitational one must be bigger. So we have Fg, and we have our air resistance, Fd. Okay, so we know for the net force in this y direction here, we have positive Fd minus Fg, or plus negative Fg. And we know Fg has to be bigger, so we know that our net force is going to be negative because we're falling downward in the downward direction. So if we were to add these together, we would get a negative net force, okay? A negative net force because we're accelerating in the negative direction. We're speeding up in the negative direction. Good?